All right, our last section for Module 3 is Section 2.5. I'm going to go ahead and put up the same disclaimer that I did for Lecture 16. That will also apply to 17 and 18. All of the formulas that you're about to see in these lectures are formulas that you do not need to memorize. These are ones that are going to be provided to you. That said, you're going to notice with this particular section that we need to pay attention to which formulas work in which instances and which ones we need to apply given the circumstances that we find ourselves in and the end goal. So just because you don't have to memorize the formulas themselves doesn't mean you shouldn't be paying special attention to exactly when you need to apply them. So this particular section, as I mentioned, is going to be split into two parts because we have quite a few formulas to pick up. You see here that the title is multiple angle and product of sum formulas, but really that doesn't even cover half of what we're going to talk about. Here is a better breakdown of what we're going to see in this section. We have a total of 5 objectives, only 4 of which are we going to tackle. The first one, we're going to use what's known as the multiple angle formulas to rewrite and evaluate trigonometric functions. We're also then going to use power reducing formulas to rewrite and evaluate trigonometric functions. That's going to be this in Lecture 17. In Lecture 18, to close out Module 3, we're going to use what are known as the half angle formulas to rewrite and evaluate trigonometric functions. I hope you're seeing a pattern here. And finally, we're going to use the product to sum and sum to product formulas to rewrite and evaluate trigonometric functions. The one objective that we won't be tackling is using trigonometric formulas to rewrite real-life models. We've seen plenty of this in previous modules, and we will see plenty of it going forward. So for the time being, we're just going to focus on the formulas themselves without a real-world context to help figure out when we need to apply them. We want to understand things in the abstract before we worry about applying them to real-world examples. So for the first half here in Lecture 17, we're going to jump straight into things with the multiple angle formulas. Now, the multiple angle formula is something that I've talked about a little bit in a previous lecture here. When we see multiple angle, we're specifically talking about it's a multiple of a given angle. So in this case, we've talked about things that are things like sine of k times u or cosine of k times u, where k is some coefficient attached to things. That is the first thing that we're going to talk about. We're also going to see things that, again, follow these other bullet points that you see listed here. These are other angle formulas that we've been talking about. Category 2 are what are going to be our power reduction formulas. 3 will be the half angles, and finally 4 that will close out Module 3, deal with what we call the sum to product and product to sum formulas. But for right now, our first focus is on Category 1. Functions of multiple angles such as sine of k times u and cosine of k times u. Category 2 will be handled in the second half of Lecture 17, and these two in 3 and 4 will be handled in Lecture 18. So, first up, the multiple angle formulas. We have specifically what are called the double angle formulas, and they are not lying here when they say these are used often in trigonometry and calculus. These are ones that you want to have a good grasp on. I mentioned this in the previous lecture, that I would point out specific formulas that even though you don't have to memorize them for trigonometry, you should consider memorizing them for later courses. Add these to the list. Sine of 2u is equal to 2 sine of u cosine of u. Tangent of 2u is equal to 2 times the tangent of u over 1 minus tangent squared u. And as for cosine 2u, this is the one that shows up the most frequently, and we actually have 3 varieties here. Cosine of 2u equals cosine squared u minus sine squared u. This is not our Pythagorean identity. It's in fact the difference of these two, with cosine in front and sine going second. 2 cosine squared u minus 1 as a different variety, and 1 minus 2 sine squared u as an alternative as well. So where do these other two come from? They come from primarily replacing either cosine squared u or sine squared u with an equivalent expression by the Pythagorean identity. So for example, sine squared u can be replaced with 1 minus cosine squared u. If you do that, this negative will apply to both, which is where you get a negative 1 and a second positive cosine squared u, which is where this expression comes from. Same thing here. If you replace cosine squared u with 1 minus sine squared u, you get a positive 1 and an additional negative sine squared u, which is where this one comes in as well. Now, this is something that I've mentioned in the past, but I wanted to kind of bring it forward. one thing you may or may not have picked up on, anytime I say the Pythagorean identity, I always say cosine squared plus sine squared equals 1, unless I'm following from the textbook. And the reason for that is that's how I was taught it, because it makes it easier to remember the order on the double angle formula for cosine. Because since this is a difference, order is very important. Cosine needs to go first, and sine needs to go second. So just kind of keep that in mind. If you've memorized the Pythagorean identity as sine plus cosine, just kind of keep in mind that it's flipped for this double angle formula. All right, that's enough about sidebars and caveats. Let's talk a little bit more about how something like this would actually be utilized. And for that, I'm going to pull us over to the notepad, and we're going to work on a problem. So the problem that we're going to be given here is we're trying to solve a trigonometric equation. Fancy that. That is the important part of Module 3 and kind of our entire focus. But there's going to be a little bit of a snag. See, we're solving the equation 2 cosine of x plus sine of 2x. This in and of itself, we can see already has a complication because we have two different trig functions, cosine and sine. And apart from that, well, one of these actually has a different angle. This is cosine of x, but this is sine of 2x. So that actually is going to create its own separate headache that we need to be aware of. This is why we need things like the double angle formulas to make things a little bit easier on ourselves. In this case, since it's sine of 2x, we're going to apply the double angle formula for sine. This is going to then split, I say split, it's not really splitting so much as it is changing, into 2 sine of x now times cosine of x. Sine of 2u equals 2 sine u times cosine u. Now this might not look that much better, but the fact that we're now all dealing with the same angle makes things a lot better for us overall. In fact, if we're looking here, now that this is a product, this actually allows for factoring. These both have a common factor of 2 cosine of x. So we'll factor that out of both parts. That'll leave us with 1 plus sine of x on the inside. Oh, and look at that. We're set equal to 0. This means that we can apply our zero product property here to solve. Let's trace our steps here. We use the double angle formula to go ahead and replace sine of 2x with 2 sine x cosine x. And then we used our algebra and factored. And now we're going to use our zero product property to keep it going. Take each one of these factors and set them equal to 0. 2 cosine of x equals 0. And 1 plus sine of x equals 0. Solve each one independently. We have cosine of 0 here, because dividing by 2 doesn't change the value. And subtracting 1 from both sides gives us sine of x equals -1. Now all we need to do is find the values where these statements are true. In this case, for cosine of x equal to 0, we know that this occurs in two different places. This occurs at pi over 2 and at 3 pi over 2. These also should have their general form, so plus 2 pi n, plus 2 pi n. And it just so happens that we actually have an overlapping solution in the case of our sine, since sine of x equals -1 when x is equal to 3 pi over 2 plus 2 pi n. So this actually matches with this one, in which case we can write our solution set simply as pi over 2 plus pi n. This might seem a little bit strange, but in this specific sense, because pi over 2 and 3 pi over 2 are separated by a pi interval, we can actually just say that we're dealing with an integer multiple of pi added to pi over 2. And since this solution and this solution are identical, they're basically lumped into one. You'll notice that in the slides they go ahead and write them out as two separate solutions, which is fine too, but this is the most efficient way to write our final answer. So we had our new addition of the double angle added into our previous work that we've already done dealing with how to solve trigonometric equations. In other words, use our different techniques to isolate the trig functions. In this case, our double angle led us to being able to use algebra, which led to us being able to use the zero product principle to isolate each of these ones separately.